Unwrap mosaics are a powerful extension of a venerable video editing paradigm, so much so that we refer to them as a new representation for the editing of video. We would like to edit video of 3D surfaces which move and change their shape over time. For example, we might want to take this video of a talking head and add features such as a moustache, rouge on the cheeks, and beetly eyebrows. Applying such edits using current video editing technologies is difficult because of the deforming surface, the handheld translating camera, and because of occlusion, the fact that each frame of video sees only a portion of the actor's face. Or we might take this video. A giraffe patrols the savannah, its neck undulating as the camera pans across the scene. Here the edits are rather unrealistic in order to demonstrate the technique. We add a symbol to the giraffe's cheek and a logo on its neck and flank. Here we wanted to make the giraffe's neck shrink and expand. Segmenting the layers is an easy manual process, but where the neck shrinks, we need to fill in the newly revealed background pixels by copying pixels from other parts of the sequence. A hint at our new representation is given by this last task. Because the camera is panning, the motion of the background between any pair of frames is accurately modelled by a plane perspective transformation or homography, and it is easy to create a mosaic which represents the entire background at once. Editing the mosaic, for example by inserting some historic buildings and 2 tigers, re-rendering the mosaic with the original motion, and replacing the foreground layers, allows us to make modifications which apply to the entire video in one simple operation. For this task, mosaic creation was easy for 2 reasons. The camera is panning, and the background is, for the most part, rigid. Our paper shows how we can build mosaics for general deforming objects with general camera motion. We shall see later how the mosaic is computed, but let us first see how it is used for editing. Here we see the unwrapped mosaic extracted from the face sequence we looked at earlier. An artist paints directly on the mosaic this edit layer of moustache, eyebrows and cheeks. Then we re-render the layer into the sequence using the warp field associated with the mosaic. Here we show the edit layer being emphasized as the edited mosaic is warped to match the motion of the original sequence. Now let's look at the extraction of the mosaic from a video sequence. We begin as we might in computing a planar mosaic by focusing computation on interesting patches in each frame and tracking these patches from frame to frame. This gives us 2D trajectories, one per patch, which can be viewed as points in a high-dimensional vector space, one projection of which is visualized here. To discover the mosaic's coordinate system, we compute a nonlinear projection or embedding of this space into 2D. Positioning the source image patches at their embedded coordinates, we can already see the outline of a face. However, for editing we will need a dense mapping. To recover a dense mosaic, we discard the patches and use the 2D points to define a warp field between each input image and the mosaic. Inverse warping each input image generates a new sequence which is approximately registered into the mosaic coordinate system. Although the registration contains many errors, each mosaic pixel is represented in many frames so that conventional panoramic stitching using graph cuts gives a seamless mosaic. It is a happy characteristic of our method that if the mosaic looks good, it is good, because we can now refine the original mapping by matching directly from the mosaic to each input image. For the giraffe, the extracted mosaic contains both the side and front of the head. Applying this edit layer creates the sequence we saw earlier. This sequence is a little harder, mainly due to blur. The boy is manually segmented from the background, automatically tracked, and an embedding is computed. Like the face, the inverse mapping is approximately registered, but contains some large errors. Unlike the face, however, stitching does not generate a perfect result, with the actor's right ear appearing doubled in the mosaic. We provide a simple user interface to repair such errors. The user scrubs through the registered sequence, finds a frame where the ear appears correctly, indicates the correct pixels, and recomputes the stitching with the constraint that the indicated pixels are untouched. Again, applying garish paint effects, we re-render and view the composited sequence. At the limits of what we can do, this rotating toy has protruding arms and cylindrical topology. The mosaic represents the torso and legs reasonably well, but truncates the tail and arms. And the repetition of the right arm also shows that we have not currently implemented cylindrical topology for the embedding space. This sport sequence is complicated by the spray, by motion blur, and by the repeated texture on the wetsuit. The recovered mosaic does not include the actor's back and contains 2 copies of his legs. We end with a few more examples of the technique in use. This cliff sequence shows that Unwrap mosaics can cope with zoom, and also that Unwrap mosaics might offer advantages even for tasks which traditional effects software handles well. Although the sequence would be hard for current systems based on planar mosaics, it would be an easy job for today's 3D animation and match moving packages. With Unwrap mosaics, however, the user interaction can be very much simplified. Compute the mosaic, paste on some photos, and re-render. The lighting is wrong, the geometry is basically flat, but the overall effect is not bad, and the whole process is simple enough that one might imagine home users making such animations, something that's not really conceivable with today's 3D packages. The final sequence is another face example. The two musicians are segmented into separate layers, and a mosaic is computed for each. The foreground leaf is also placed in its own layer. Painting the mosaic and re-rendering all the layers gives a convincing animation with all occlusions correctly handled. Of course, not all edits need be augmentations. We can also edit the mosaic to remove or paint out features, as this final example illustrates. Mosaics have been around for a long time, but until now they have been useful only in the special cases of planar objects or panning cameras. We hope that by unwrapping the representation, and by providing a robust algorithm to extract the unwrapped mosaics, this intuitive editing paradigm can enjoy much broader application.